We're going to talk about note card 47, rules for exponents or laws for exponents. And before we start going through the examples, we have to remember that if we have an exponent like a to the power of 4, you have to remember that the bottom, the big part, is the base, and the exponent is the power. Okay? And if you can remember that, all of this should make sense. So number one, we're multiplying bases that are the same. And when you multiply bases that are the same, you add the powers. So this becomes x to the a plus b. Here's an example. If I have x squared times x to the 7th, I'm multiplying bases that are the same, so I add the powers and I get x to the 9th. Number two, if I'm dividing bases that are the same, I subtract the powers. So this becomes x to the a minus b. So here's an example. X to the 10th divided by x to the 3rd is x to the 10 minus 3, which is x to the 7th. Number three, if I have a single term with a power inside parentheses and another power outside the parentheses, the law says to multiply the two powers. So this becomes x to the a times b. And so the example, I have more than one term. I have a 2 and an x to the 4th. The power of this 2 is 1. So I multiply, because there's multiplication inside here, multiplication or division this works with. If there's addition or subtraction inside, it does not work. This rule does not apply. But here I have multiplication. So I multiply the power of 3 to the power of 1 and the power of 3 to the power of 4, which gives me 2 to the power of 3, x to the power of 12, and 2 to the power of 3 is 2 times 2 times 2, which is 8. So I get 8x to the 12th. Number four, if I have a negative exponent, what happens here is you can make any number or variable a fraction, and you make it a fraction by putting it over 1. And whenever you have a negative exponent, what happens is you need to move it to the other side of the fraction bar, and it becomes positive. So this goes to the bottom of the fraction bar with a positive exponent. If everything leaves the top, then you leave a 1 there. If everything were to leave the bottom, like on number 5 here, you would leave a 1 on bottom. So this would be over 1, but anything over 1 is itself. So let's look at these two examples here. I have x to the negative 5th, make it a fraction by putting it over 1, and it becomes 1 over x to the power of positive 5. Number 5's example, I have 1 over x to the negative 6th. This goes to the top of the fraction with a positive exponent, and it becomes x to the power of positive 6 over 1, or just x to the power of positive 6. Have a couple of more examples here. These examples deal with something that we talked about in Algebra 2. If you have x to the power of p over q, this is equal to the q root of p, q root of x to the power, all in parentheses, to the power of p, which is also the same as the q root of x to the power of p. Now there's three equivalent expressions here. The one that I like the best is this one, and the reason why I like it the best is because it's very beneficial, and I'll show you in a second what I'm talking about. But you have to recall your p's and q's. Okay? So what I have here, if I recall my p's and q's, if the q is not there, the index number, if the q is not there, that means there's really a 2 here, or there's a square root. Okay? And so what I'm looking for, and I'm going to try to break this down into very simple terms here. When your index number tells you how many groups you're looking for. Okay? So since my index number is not here, that tells me that it's a 2, which tells me that I'm looking for groups of 2. And I can rewrite this square root of x to the 6th as square root of x times x times x times x times x times x. This is x to the 6th. I'm looking for groups of 2 because my index number tells me how many, what size of groups I'm looking for. So I want to circle my groups of 2. I have 3 of them. If everything gets circled, then your radical goes away. If it's circled, it comes out one time. I have one circle here, that comes out once. I have one circle here, that comes out once. I have one circle here, that comes out once. And what I'm left with is x to the 3rd. That's how that works. Let's look at another one. My index number's not here. That tells me I have a 2 there, which means I'm looking for groups of 2. So I have 10 x's. Looking for groups of 2. 1, 2, 3, 4, 5. Everything's circled, so my radical is going to go away. And I have 5 x's that come out. X, 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 which is x to the 5th. Let's look at the next example. Here, my index number is still 2. I have 9 x's. If you don't want to write it out like this, you could just write it out like this, where you have 8x to the 8th and 1x left. And you can divide that 8 by 2 and you get x to the 4th out there. That might be easier for some of you. Otherwise, do it like this. Looking for groups of 2. Okay, so I have 1, 2, 3, 4 x's that come out. There's my x to the 4th. And this x didn't get circled, it stays in. That's why I have x to the 4th times root x. Okay, continuing on. Okay, number 6, I have x to the power of 1/2, and I can write that as a radical because p is 1. P is 1, and q is 2, because it's x to the power of p over q. So p is 1, q is 2. My q is my index number, it's 2. It's missing, that tells me it's 2. And p, the power of 1, it's going to go right here, which if I put a power of 1, I don't need to. So this is the same thing as saying x to the 1/2 is the same thing as saying square root x. Here's another example. Have 16 to the power of 1/2, which is square root of 16, because p is 1, power of 16 is 1. My index number is 2, it's not there. And the square root of 16 is 4. Number 7, p is 1, q is 3. So that's the cube root of x to the power of 1, or just the cube root of x. Here's an example. Earlier we talked about when you have a power outside the set of parentheses with multiplication. I also mentioned division. We have division going on here. The rule applies the same way. I skipped a step here. Let me put an intermediate step in here. This actually becomes the power of 8 is 1, the power of 27 is 1. So I have to multiply the 1/3 power out here to each power inside. So this becomes 8 to the power of 1/3 over 27 to the power of 1/3. And using p's and q's, p is 1, q is 3, this becomes the cube root of 8 over the cube root of 27. And you may or may not know what the cube root of 8 is. It's 2. The cube root of 27 is 3, and my answer is 2/3. If you didn't know that, what you could look at is prime factorization. If I did and I'm going to do this one time. This is a quick review. If I'm looking at the prime factorization of 8, I know that my prime numbers, I have 1, 2, 3, 5, 7, so on. I start with the easiest ones. I don't want to divide by 1. This is divisible by 2 here. Okay, so I have 4 times 2. 2 is prime, circle it. Then I have 2 times 2, and these are prime, circle it. So I'm looking for, I have the cube root of 2 times 2 times 2, looking for groups of 3, circle it, the 1, 2 comes out, everything circled, the radical goes away. That's how I get the cube root of 8 is 2. Same with the 27. If I want to look at the prime factors of 27, it's divisible by 3. So that's 3 times 9. The 3's prime, circle it. 3 times 3. Those 3's are prime, circle it. So I have the cube root of 3 times 3 times 3. Looking for groups of 3, circle it. It's all circled. The radical goes away. The cube root of 27 is 3. That's my answer. Number 8, I have x to the power of 3 halves. Here, p is 3 and q is 2. So that's going to be the square root, because q is my index number, to the power of 3. Another way to write that is the square root of x to the third. And if you recall what I asked you to write down about p's and q's, you will see that these two expressions are the same, because I could write it as, and you should write this on your paper, that x to the power of p over q is equal to the q root of x to the power of p is also equal to the q root of x to the power of p. And again, I will say that this is the one that is very beneficial when we start working out some problems in a second. That's the one I prefer to use all the time. Another way to look at it is that when you have these fractional exponents here, the denominator is the root or index number, and the numerator is the power. Continuing on, I have x to the power of 2/3. Oh, missed this example up here. 25 to the power of 3 over 2. The q, or the index number, is 2, which means I have square root, and the power is p, power of p, which is 3. So I have the square root of 25, all of that to the power of 3. Everybody knows the square root of 25 is 5, and 5 to the third is 25. That's how you simplify that. Number 9. Q is 3, p is 2. So this is the cube root of x to the power of 2, or the cube root of x squared. It's the same. Example 27. We have 27 to the power of 2/3. Q is 3, p is 2. Cube root of 27, we found out up here, is 3. And 3 squared is 9. So 27 to the power of 2 over 3 is 9. Number 10, a couple of ways to look at it. Let's just look at it how it's written right here. Remember, if I have division inside and a power outside, I have to multiply this power to every power inside. Well, these powers are 1. So this could become x to the negative 3/4 over y to the negative 3/4, which would become y to the positive 3/4 over x to the positive 3/4, which becomes what I have here. Or you could just skip these two steps and go from, if I have a negative power, I could just flip my fraction inside and make my power positive out there. It's the same thing. So I went from x over y to the negative 3/4 to y over x to the positive 3/4. Here's an example of that property. I have 16 over 81 to the negative 3/4, which is 81 over 16 to the positive 3/4. My next step, which I don't show here, I will show you. My next step from right here would have been 81 to the power of 3 over 4 over 16 to the power of 3 over 4. And I can't simplify these without converting them to these radicals. My index number q is 4, that's why I have the 4th root on both of those, to the power of 3. That's why it's out here like this. The fourth root of 81 is 3. How could I know that? Do your prime factorization of 81. I'm going to do this one more time. I know that 81 is divisible by 9. So I'm going to go ahead and do 9 times 9. Now neither one of those are prime, so I'm not going to circle them. But these both becomes 3 times 3 and 3 times 3. They're all prime. Circle it. So I'm looking for the fourth root, or groups of 4, of 3 times 3 times 3 times 3. It's all circled, which means the radical goes away, and the fourth root of 81 is 3. So I have 3 to the third, because I have to do this to the power of 3 out here. The fourth root of 16, doing it the same way, is 2, because 2 times 2 is 4, times 2 is 8, times 2 is 16. So the fourth root of 16 is 2 to the power of 3, because I have this power of 3 out here. 3 to the third is 27, 2 to the third is 8. My answer is 27 over 8. And that's how you do those. That's a quick review of exponents and laws of exponents. Note card 47B is just another way of talking about negative exponents, but I believe we covered negative exponents well on note card 47. But let's just look at note card 47B quickly. Negative exponents. This is note card 47B. For most problems, change negative exponents into positive exponents before simplifying further. How do you do that? If you have a negative exponent in the numerator of a fraction, then move that term to the denominator and make the exponent positive. Example, have x to the power of negative 2 on top. It simply moves to the bottom with a positive exponent. B says if you have a negative exponent in the denominator of the fraction, then move that term to the numerator and make the exponent positive. In this example, I have z to the negative 4 in the denominator. I move that to the top and it becomes z to the power of positive 4.